Hello everyone, this is video 9.7. We're going to be looking at linear and other relationships. Interesting title. And so we're going to be pulling forward a lot of the ideas we looked at in section 9.5 and 9.6. So I don't know why you might be watching video 9.7 first, but make sure you go back and watch 9.5 and 9.6 first. A lot of the ideas and a lot of the definitions are established in those sections before we get into this section. So let's get started. So a couple of definitions, even though the first one should be pretty familiar. We've already looked at a linear relationship, and we've already looked at a function. So now we're just going to put those ideas together and create a linear function, which is a function whose graph lies on a straight line. Is a little bit redundant because every linear relationship is going to be a linear function. As soon as it's linear, it has to be a function. I will let you try to work through the reality of that, but you can't draw a straight line where an x value has two y values. It would have to bend back to hit that x value again. And then once it bends, it's no longer a straight line. So it's a little bit of a redundancy, but it's not the worst thing in the world. I just don't want you to try to spend too much time on what's the difference between a linear function and a linear relationship. There's not really one. Everything linear is a function. We do have one new term, though, this idea of the slope. And I've put some parts here in italics. This is my emphasis, not the books. So we've got the constant rate of change. Now, we've talked about rate of change quite a bit in the previous sections. And we mentioned that for a line, that rate of change has to be constant. This is one of the last things we talked about in 9.6, where we had a function where the rate of change was increasing or decreasing. Something was uh, something was increasing but at a decreasing rate. So the slope is the constant rate of change. If something is a line, it has a rate of change that's constant, and that value we're going to call the slope. And so we have in a linear relationship slash function. Again, I just mentioned every linear function is a linear relationship and vice versa. And if it's linear, it has to have a constant rate of change. So again, there's a lot of redundancy built into this, but that's not the worst thing. We're going to call that value the slope. Now, some of you might remember slope as rise over run, and there's nothing wrong with that. But rise over run is just like something that people say, but they don't always understand what that means necessarily. So we want to be talking about slope not just from a computational standpoint, but from a conceptual standpoint. Like, what does it really mean? If you can calculate the value, the slope is 2/3. Okay, but what does it mean? I have no idea. That's what we want to avoid. So I don't want you and you don't want your students to be able to find the numerical value of something, but not be able to describe it or explain it or say what it is or see what it is given something. So we're going to work through a little bit of this today so we have a little bit better idea of what the slope is and what it looks like in a graph. So one more thing to tie into this is this idea of a y-intercept. And the y-intercept is going to be where the function hits the y-axis. It's intercepting the y-axis. So we've already seen that the x-axis is going to go across. So let's go here. So here's my x-axis, and here's my y-axis. And so the y-intercept is going to be where it hits this y-axis, the vertical axis. It's also going to be where x equals 0, which should make some degree of sense because the y-axis is going to be where x equals 0. The x-axis is going to be where y equals 0. And this can be a little confusing for students learning this the first time because we're saying the y-axis is where x equals 0. And so, well, we're talking about y here, but x there. If we take a second and draw the picture and look at it, we can see that this y-axis is going to be the line where x equals 0, and the x-axis is the line where y equals 0. So I'll put in x equals 0 here and y equals 0 there. This was the last problem. This is the checkpoint problem to section 9.6. So theoretically, if you already did this problem, you already know sort of what's going to happen with this. If you didn't, then let's go through and look at some values here. I'm going to make my table. So when x equals 0, I get negative 2 times 0 is 0, plus 3 makes 3. So I can go ahead and graph x equals 0, y equals 3. So this is my point 0, 3. I can put in x equals 1. So now it's going to be negative 2 times 1 is negative 2. Negative 2 plus 3 equals 1. So when this is 1, this is 1. When x is 1, y is 1. And then we'll throw in a negative 1 just for good measure. So negative 2 times negative 1 is a positive 2. Negative times a negative makes a positive. That's a positive 2 plus the 3, and that makes a 5. So this is a 5. So now we can see a couple of things here. Number one, we can see that our y-intercept here is going to be the point 0, 3. Now, sometimes you'll see the y-intercept equals 3. You want to be really specific on how you're asking for this. Are you asking for the y-intercept as a point? If you're asking for the y-intercept as a point, then we're looking for the point 0, 3. We need to give both values. Later on, students will know that this is going to be where x equals 0. So we can just say the y-intercept is at 3 or at b equals 3. And we don't need to give both values because we know the x value is a 0. We'll talk about this b and why it's a b here in a moment. But just be very, very clear with your students what you're asking them to give. If you want them to give that to you as a point or give it to you as a value. My recommendation would be when they're first seeing it for the first time, ask for it as a point. Because if they give the point 1, 1, you can tell right away why it's wrong. Because they're not looking where x equals 0, they're looking where x equals 1. They found a point off the axis. If you ask for it just as a value and they just say, okay, well, the y-intercept is 1, you have a really hard time figuring out how or why they got that wrong. So I would really recommend that you ask for it as a point, although technically you could ask for it as a value. So we see the y-intercept here. We also can see, and I'll go back to blue here, that as the x increases, the y is decreasing by negative 2. So as my x increases by 1, my y decreases by negative 2. And this is my slope. This is my constant rate of change. So we can see here in this formula, in this equation, we can see the slope and the intercept, which we're going to talk about here in a moment. But this is one of the things that I wanted you to look at in the previous section, was hopefully that you would see that the slope is a constant, that the slope is a constant value of negative 2, and that it hits this axis here at 3, at the point 0, 3. Now, where it crosses the x-axis, we don't need to worry about so much. We're not going to talk about x-intercepts in this class too much. Although if you want to figure out where that is, you can either see that it's about, that it's 1.5, or you could solve through it algebraically if you want to. But for right now, we're just going to worry about slopes and y-intercepts. So we kind of hinted at this in the previous slide. We have this idea of the slope-intercept form. And this is your y equals mx plus b. How much you want to really talk about with your students the specifics of this form, is going to be up to you, and it's going to be dependent on the maturity and sophistication of the students that you have. We can do finding the slope and finding the y-intercept without ever talking about this in this form or generalizing, this form in this algebraic way. The book goes through an interesting little picture here where they take this point B, which is our intercept, and then finds some points. So this would be 1, this would be 2, this would be 3. And so as this goes over 1, this is going to go up m. And so this is my constant rate of change m. And so as this line goes, This is always increasing by m. Now, this m could be negative and it doesn't really change anything. We're assuming for the sake of this picture that it's a positive, but it could be positive or negative. And so then this point, we know this would be 1, and then this, the x value is 1, and so then this value here would be b plus m. And then this value would be 2, and now this would be b plus 2m. And then this value would be 3, and this would be b plus 3m. And so if you're having a hard time seeing where all these m's are coming from, we know, if we carry this over, we know this distance was b, and then each of these steps was m. So if we add all these together, I've got b plus m plus m plus m, which is b plus 3m. If I go out to some point x, then this value here is going to be my x value, and now my y value is going to be b plus mx. So I'm going to have as many m's as I have x values. I mean, if you're kind of lost on this, that's fine. I like this picture. I think it explains a lot. I don't know if you necessarily need it or not, so this is sort of a target of opportunity. If this makes sense to you and this helps you, cool. If this is not making an awful lot of sense to you, that's okay. As long as you can still work through this equation, as long as you can still explain what the slope is and explain what the intercept is, this sort of generalized algebraic approach is nice, but not really necessary for this class. If you're going to be doing middle school, if you're going to be adding on a middle school endorsement to this, then you might want to make the effort to really understand what's going on in this diagram. But for the sake of this class, you're probably okay with just being able to explain the slope, explain the intercept, draw the picture, show where the slope and intercept are in your graph. That's probably more than enough. So the book mentions these 3 other types of relationships, and we're just going to go over these very, very quickly for various reasons. Number 1, inversely proportionate. This is covered mostly in 137, so if you haven't had 137 yet, this is probably not going to make an awful lot of sense. But I'll tell you that the graph looks something like this. A quadratic function, we're not going to talk about hardly at all in this class. This may be the first and last time this really gets mentioned, but I will tell you that it looks like a U-shaped curve, like this. Some of you may recognize this as a parabola. If not, that's okay. But we see that it's a curvy thing like this, and it could curve up or down. It could curve down like this, but it's a U-shaped curve. And then we have our exponential functions, which look something like this. Now, this exponential is the same as a geometric function. And we mentioned geometric sequences earlier on in the chapter in 9.5. So if you go back and look at some of those functions, they have this sort of graph. Now, the one thing I want you to take away from these 3, how does linear compare to these? Well, linear is a straight line, and these are not straight lines. That's really the basics that we really need you to understand at this point. If you've had 137, then you can probably make a little bit more detailed of a comparison about inversely proportionate and linear. If you really paid attention in section 9.5 and it made a lot of sense to you, you can probably get into a lot more detail with the geometric, with the exponential functions, specifically about the rate of change not being constant. In an exponential function, the rate of change is going to be changing. It's going to be dynamic instead of constant. Quadratic, we're just not going to talk about. If you know anything about quadratic functions, if you've seen those before, if you remember that from previous math classes, cool. If not, that's cool too. The book goes into what's happening with quadratic functions, that the rate of change is changing by a constant rate of change. So The differences are changing, but the differences between the differences is constant. It's really neat. It's really cool. You can look at it on your own, but we're not going to talk about that too much in this class. So the main thing for what we're doing right now is just knowing that these these three types, inversely proportionate, quadratic, and exponential, they don't form straight lines. They're not linear. That's the bulk of what you need to know for right now. So for your checkpoint problem, I want you to go back and look at linear functions. Is it possible for a linear function to have zero y-intercepts? Is it possible to have one y-intercept? Is it possible to have two y-intercepts? And then also, is it possible for it to have 0, 1, or 2 x-intercepts? So you may want to try to draw those lines in various ways and see which of these is possible. I'll leave that for you to work through. If any questions on this problem, as always, bring them into class and we'll talk about them in class. All right, thanks. See you.